All right, so welcome to the third tutorial session. This one's on generative adversarial networks. So it is my great pleasure to introduce Dr. Ian Goodfellow. He did a master's and a bachelor's at Stanford University, finishing there in 2009, at which point he moved to the University of Montreal, where he did a PhD with Yoshua Bengio and I. And after that, he moved to the Google Brain group at that same year. And after that, he moved just recently, earlier this year, to the OpenAI, where he currently is. So I think that Ian is quite simply one of the most creative and influential researchers in our community today. And I think that we have a room full of people ready to hear about a topic, GANs, or Generative Adversarial Networks, that he invented 2 years ago in a bar in Montreal, I might add, is testament to that. So without further ado, I give you Ian Goodfellow. Yeah, I forgot to mention, he's requested that we have questions throughout, so if you actually have a question, just go to the mic and he'll maybe stop and try to answer your question. I'll try not to do that again. Okay, go ahead.
Thank you very much for the introduction, Aaron. Thank you, everybody, for coming today. Let me tell you a little bit about the format here. Despite the size of the event, I'd still like it to be a little bit interactive and let you feel like you can make the tutorial what you want it to be for yourself. I believe a lot that the tutorial should be a chance for you to get some hands-on experience and to feel like you're building your own mastery of this subject. So I've included 3 exercises that will appear throughout the presentation. Every time there's an exercise, you can choose whether you want to work on it or not. I'll give a little 5-minute break, since I know it's hard to pay attention to a presentation for 2 hours straight. And if you'd like to work through the exercise, you can work through it. Otherwise, just take a break and chat with your neighbors. The basic topic of today's tutorial is really generative modeling in general. It's impossible to describe generative adversarial networks without contrasting them with some of the other approaches and describing some of the overall goals in this area that we're working on. The basic idea of generative modeling is to take a collection of training examples and form some representation of a probability distribution that explains where those training examples came from. There are 2 basic things that you can do with a generative model. One is you can take a collection of points and infer a density function that describes the probability distribution that generated them. I show that in the upper row of this slide, where I have taken several points on a one-dimensional number line and fitted a Gaussian density to them. That's what we usually think of when we describe generative modeling. But there's another way that you can build a generative model, which is to take a machine that observes many samples from a distribution and then is able to create more samples from that same distribution. Generative adversarial networks primarily lie in the second category, where what we want to do is simply generate more samples rather than find the density function. As a brief outline of the presentation today, I'm first going to describe why we should study generative modeling at all. It might seem a little bit silly to just make more images when we already have millions of images lying around. Next, I'll describe how generative models work in general and situate generative adversarial networks among the family of generative models, explaining exactly what is different about them than other approaches. Then I'll describe in detail how generative adversarial networks work, and I'll move on to special tips and tricks that practitioners have developed that are less theoretically motivated but seem to work well in practice. Then I'll describe some research frontiers, and I'll conclude by describing the latest state-of-the-art in generative modeling, which combines generative adversarial networks with other methods. So the first section of this presentation is about why we should study generative models at all. Most of the time in machine learning, we use models that take an input and map that input to a single output. That's really great for things like looking at an image and saying what kind of object is in that image, or looking at a sentence and saying whether that sentence is positive or negative. Why exactly would we want to learn a distribution over different training examples? Well, first off, high-dimensional probability distributions are an important object in many branches of engineering and applied math, and this exercises our ability to manipulate them. But more concretely, there are several ways that we could imagine using generative models once we have perfected them. One is that we could use the generative model to simulate possible futures for reinforcement learning. There are at least two different ways that you could use this. One is you could train your agent in a simulated environment that's built entirely by the generative model, rather than needing to build an environment by hand. The advantage of using this simulated environment over the real world is that it could be more easily parallelized across many machines, and that mistakes in this environment are not as costly as if you actually make a mistake in the physical world and do real harm. Similarly, an agent that is able to imagine future states of the world using a generative model can plan for the future by simulating many different ideas of plans that it could execute and testing which of them works out as best as possible. There's a paper on that subject with Chelsea Finn as the first author where we evaluated generative models on the robot pushing data set to start working toward this goal of using generative models to plan actions. Another major use of generative models is that they are able to handle missing data much more effectively than the standard input to output mappings of machine learning models that we usually use. Generative models are able to fill in missing inputs, and they're also able to learn when some of the labels in the data set are missing. Semi-supervised learning is a particularly useful application of generative modeling, where we may have very few labeled inputs, but by leveraging many more unlabeled examples, we are able to obtain very good error rates on a test set. Many other tasks also intrinsically require that we use multimodal outputs. Rather than mapping one input to a single output, there are many possible outputs, and the model needs to capture all of them. And finally, there are several tasks that just plain require realistic generation of images or audio waveforms as the actual specification of the task itself. And these clearly require generative modeling intrinsically. One example of a task that requires multimodal outputs is predicting the next frame in a video. Because there are many different things that can happen in the next time step, there are many different frames that can appear in a sequence after the current image. Because there are so many different things that can happen, traditional approaches for predicting the next video frame often become very blurry. When they try to represent the distribution over the next frame using a single image, many different possible next frame images are averaged together and result in a blurry mess. I'm showing here some images from a paper by William Lauder and his collaborators that was published earlier this year. On the left, I show you the ground truth image, the image that should be predicted next in a video of a 3D rendering of a rotated head. In the middle, I show you the image that is predicted when we take a traditional model that is trained using mean squared error. Because this mean squared error model is predicting many different possible futures and then averaging them together to hedge its bets, we end up with a blurry image where the eyes are not particularly crisply defined. Small variations in the amount that the head rotates can place the eyes in very different positions. And when we average all those different positions together, we get a blurry image of the eyes. Likewise, the ears on this person's head have more or less disappeared. On the right, I show you what happens when we bring in a more generative modeling type approach, and in particular, when we use an adversarial loss to train the model. In the image on the right, the model has successfully predicted the presence of the ear and has successfully drawn a crisp image of the eyes with dark pixels in that area and sharp edges on the features of the eyes. Another task that intrinsically requires being able to generate good data is super resolution of images. In this example, we begin with the original image on the left, and then, not pictured, we downsample that image to about half its original resolution. We then show several different ways of reconstructing the high resolution version of the image. If we just use the bicubic interpolation method, just a hand-designed mathematical formula for what the pixels ought to be based on sampling theory, we get a relatively blurry image. That's shown second from the left. The remaining two images show different ways of using machine learning to actually learn to create high-resolution images that look like the data distribution. So here the model is actually able to use its knowledge of what high-resolution images look like to provide details that have been lost in the downsampling process. The new high-resolution image may not be perfectly accurate and may not perfectly agree with reality, but it at least looks like something that is plausible and is visually pleasing. There are many different applications that involve interaction between a human being and an image generation process. One of these is a collaboration between Berkeley and Adobe called IGAN, where the I stands for interactive. The basic idea of IGAN is that it assists a human to create artwork. The human artist draws a few squiggly green lines, and then a generative model is used to search over the space of possible images that resemble what the human has begun to draw. Even though the human doesn't have much artistic ability, they can draw a simple black triangle, and it will be turned into a photo quality mountain. This is such a popular area that there have actually been 2 papers on this subject that came out just in the last few months. Introspective adversarial networks also offer this ability to provide interactive photo editing and have demonstrated their results mostly in the context of editing faces. So the same idea still applies, that a human can begin editing a photo, and the generative model will automatically update the photo to keep it appearing realistic, even though the human is making very poorly controlled, mouse-controlled movements that are not nearly as fine as would be needed to make nice photorealistic details. There are also just a long tail of different applications that require generating really good images. A recent paper called Image-to-Image Translation shows how conditional generative adversarial networks can be trained to implement many of these multimodal output distributions, where an input can be mapped to many different possible outputs. One example is taking sketches and turning them into photos. In this case, it's very easy to train the model because photos can be converted to sketches just by using an edge extractor, and that provides a very large training set for the mapping from sketch to image. Essentially, in this case, the generative model learns to invert the edge detection process, even though the inverse has many possible inputs that all correspond to the same output, and vice versa. The same kind of model can also convert aerial photographs into maps, and can take descriptions of scenes in terms of which object category should appear at each pixel, and turn them into photorealistic images. So these are all several different reasons that we might want to study generative models, ranging from the different kinds of mathematical abilities they force us to develop, to the many different applications that we can carry out once we have these kinds of models. So next, we might wonder, how exactly do generative models work? And in particular, how do generative adversarial networks compare in terms of the way that they work to other models? It's easiest to compare many different models if I describe all of them as performing maximum likelihood. There are, in fact, other approaches to generative modeling besides maximum likelihood, but for the purpose of making a nice, crisp comparison of several different models, I'm going to pretend that they all do maximum likelihood for the moment. The basic idea of maximum likelihood is that we write down a density function that the model describes, that I represent with p model of x. X is a vector describing the input, and p model of x is a distribution controlled by parameters theta that describes exactly where the data concentrates and where it is spread more thinly. Maximum likelihood consists in measuring the log probability that this density function assigns to all the training data points and adjusting the parameters theta to increase that probability. The way that different models go about accomplishing this is what makes the models different from each other. So among all the different models that can be described as implementing maximum likelihood, we can draw them in a family tree, where the first place where this tree forks is we ask whether the model represents the data with the density with an explicit function or not. So when we have an explicit density function, it looks exactly like what I showed on this previous slide. We actually write down a function p model, and we're able to evaluate log p model and increase it on the training data. Within the family of models that have an explicit density, we may then ask whether that density function is actually tractable or not. When we want to model very complicated distributions, like the distribution over natural images or the distribution over speech waveforms, it can be challenging to design a parametric function that is able to capture the distribution efficiently. And this means that many of the distributions we've studied are not actually tractable. However, with careful design, it has been possible to design a few different density functions that actually are tractable. That's the family of models like pixel RNN, pixel CNN, and other fully visible belief networks like NADE and MADE. The other major family of distributions that have a tractable density is the nonlinear ICA family. This family of models is based on taking a simple distribution, like a Gaussian distribution, and then using a nonlinear transformation of samples from that distribution to warp the samples into the space that we care about. If we're able to measure the determinant of the Jacobian of that transformation, we can determine the density in the new space that results from that warping. Within the family of models that use an explicit density, the other set of approaches is those that cannot actually have a tractable density function. There are two basic approaches within this family. One of these is the model family that approximates an intractable density function by placing a lower bound on the log likelihood and then maximizing that lower bound. Another approach is to use a Markov chain to make an estimate of the density function or of its gradient. Both of these families incur some disadvantages from the approximations that they use. Finally, we may give up altogether on having an explicit density function, and instead we represent the density function implicitly. This is the rightmost branch of the tree. One of the main ways that you can implicitly represent a probability distribution is to design a procedure that can draw samples from that probability distribution, even if we don't necessarily know the density function. If we draw samples using a Markov chain, that gives us one family of distributions, of models, of which the main example is the generative stochastic network. And then finally, if we would like to draw samples directly, we have models like generative adversarial networks or deep moment matching networks are both examples of models that can draw samples directly but don't necessarily represent a density function. So now let's look at each of these in a little bit more detail and describe exactly what the advantages and disadvantages of them are and why you might want to be in one branch of the tree or another. So first, fully visible belief networks are the most mathematically straightforward. They use the chain rule of probability to decompose the probability distribution over a vector into a product over each of the members of the vector. We write down a probability distribution for the distribution over x1, and then we multiply that by the distribution over x2 given x1, and then x3 given x1 and x2, and so on until we finally have a distribution over the final member of the vector given all of the other members of the vector. So this goes back to a paper by Brendan Frey in 1996, but has had several other advancements in the meantime. The current most popular member of this model family is the pixel CNN, and I show here some samples of elephants that it generated. The primary disadvantage of this approach is that generating a sample is very slow. Each time we want to sample a different xi from the vector x, we need to run the model again. And these n different times that we run the model cannot be parallelized. Each of these operations of sampling another xi is dependent on all of the earlier xi values. And that means that there's really no choice but to schedule them one after another, regardless of how much bandwidth we have available. One other smaller drawback is that the generation process is not guided by a latent code. Many of the other models that we study have a latent code that we can sample first that describes the entire vector to be generated. And then the rest of the process involves translating that latent vector into something that lies in the data space. And that allows us to do things like have embeddings that are useful for semi-supervised learning or generating samples that have particular properties that we're interested in. Fully visible belief networks don't do this out of the box, but there are different extensions of them that can enable these abilities. One very recent example of a fully visible belief net is Wavenet, and it shows both some of the advantages and some of the disadvantages of these fully visible belief networks. First, because the optimization process is very straightforward. It's just minimizing a cost function with no approximations to that cost function. It's very effective and generates really amazing samples. But the disadvantage is that the sample generation is very slow. In particular, it takes about 2 minutes to generate 1 second of audio. And that means that barring some major improvement in the way that we're able to run the model, it's not going to be able to be used for interactive dialogue anytime soon, even though it is able to generate very good lifelike audio waveforms. The other major family of explicit tractable density models is the family of models based on the change of variables, where we begin with a simple distribution like a Gaussian, and we use a nonlinear function to transform that distribution into another space. So we transform from a latent space to, on this slide, the space of natural images. The main drawback to this approach is that the transformation must be carefully designed to be invertible and to have a tractable Jacobian, and in fact, a tractable determinant of the Jacobian. In particular, this requirement says that the latent variables must have the same dimensionality as the data space. So if we want to generate 3,000 pixels, we need to have 3,000 latent variables. It makes it harder to design the model to have exactly the capacity that we would like to have. Another major family of models is those that have intractable density functions, but then use tractable approximations to those density functions. Currently, one of the most popular members of this family is the variational autoencoder. The basic idea is to write down a density function, log p of x, where the density is intractable because we need to marginalize out a random variable z. Z is a vector of latent variables that provide a hidden code describing the input image. And because the process of marginalizing these variables out to recover simply the distribution over x is intractable, we're forced to use instead a variational approximation. This variational approximation introduces a distribution q over the latent variable z. And to the extent that this distribution q is closer to the true posterior over the latent variables, we're able to make a bound that becomes tighter and tighter and does a better job of lower bounding the true density. Unfortunately, this model is only asymptotically consistent if this Q distribution is perfect. Otherwise, there's a gap in between the lower bound and the actual density. So even if the optimizer is perfect, and even if we have infinite training data, we are not able to recover exactly the distribution that was used to generate the data. In practice, we observe that variational autoencoders are very good at obtaining high likelihood, but they tend to produce lower quality samples. And in particular, the samples are often relatively blurry. Another major family of models is the Boltzmann machine. These also have an explicit density function that is not actually tractable. In this case, the Boltzmann machine is defined by an energy function, and the probability of a particular state is proportional to e to the value of the energy. In order to convert this to an actual probability distribution, it's necessary to renormalize by dividing by the sum over all the different states. And that sum becomes intractable. We're able to approximate it using Monte Carlo methods, but those Monte Carlo methods often suffer from problems like failing to mix between different modes. And in general, Monte Carlo methods, especially Markov chain Monte Carlo methods, perform very poorly in high-dimensional spaces. Because the Markov chains break down for very large images, we don't really see Boltzmann machines applied to tasks like modeling ImageNet images. They perform very well on small data sets like MNIST, but then have never really scaled. All of these different observations about the other members of the family tree bring us to generative adversarial networks and explain the design requirements that I had in mind when I thought of this model. First, they use a latent code that describes everything that's generated later. They have this property in common with other models like variational autoencoders and Boltzmann machines, but it's an advantage that they have over fully visible belief networks. They're also asymptotically consistent. If you're able to find the equilibrium point of the game defining a generative adversarial network, you're guaranteed that you've actually recovered the true distribution that generates the data, modulo sample complexity issues. So if you have infinite training data, you do eventually recover the correct distribution. There are no Markov chains needed, neither to train the generative adversarial network nor to draw samples from it. And I felt like that was an important requirement based on the way that the Markov chains had seemed to hold back restricted Boltzmann machines. Today, we've started to see some models that use Markov chains more successfully, and I'll describe those later in the talk. But that was one of my primary motivations for designing this particular model family. Finally, a major advantage of generative adversarial networks is that they are often regarded as producing the best samples compared to other models like variational autoencoders. In the past few months, we've started to see other models like pixel CNNs competing with them, and it's now somewhat difficult to say which is the best because we don't have a good way of quantifying exactly how good a set of samples are. That concludes my description of the different families of generative models and how they relate to each other and how generative adversarial networks are situated in this family of generative models. So I'll move on to describing exactly how generative adversarial networks actually work. The basic framework is that we have two different models, and they're adversaries of each other in the sense of game theory. There's a game that has well-defined payoff functions, and each of the two players tries to determine how they can get the most payoff possible. Within this game, there are two different networks. One of them is called the generator, and it is the primary model that we're interested in learning. The generator is the model that actually generates samples that are intended to resemble those that were in the training distribution. The other model is the discriminator. The discriminator is not really necessary after we finish the training process, at least not in the original development of generative adversarial networks. There are some ways of getting some extra use out of the discriminator. But in the basic setup, we can think of the discriminator as a tool that we use during training that can be discarded as soon as training is over. The role of the discriminator is to inspect a sample and say whether that sample looks real or fake. So the training process consists of sampling images or other kinds of data from the training set, and then running the discriminator on those inputs. The discriminator is any kind of differentiable function that has parameters that we can learn with gradient descent. So we usually represent it as a deep neural network, but in principle, it could be other kinds of models. When the discriminator is applied to images that come from the training set, its goal is to output a value that is near 1, representing a high probability that the input was real rather than fake. But half the time, we also apply the discriminator to examples that are in fact fake. In this case, we begin by sampling the latent vector z. In this case, we sample z from the prior distribution over latent variables. So z is essentially a vector of unstructured noise. It's a source of randomness that allows the generator to output a wide variety of different vectors. We then apply the generator function to the input vector z. The generator function is a differentiable function that has parameters that can be learned by gradient descent, similar to the discriminator function. And we usually represent the generator as being a deep neural network, though once again, it could be any other kind of model that satisfies those differentiability properties. After we have applied G to Z, we obtain a sample from the model. And ideally, this will resemble actual samples from the data set, though early in learning it will not. After we've obtained that sample, we apply the discriminator function D again, and this time, the goal of the discriminator D is to output a value, D of G of Z, that is near 0. I'm sorry, I've realized there's a mistake in the slide, actually, it's backwards. The discriminator wants to make the value in this case be near 0, and the generator would like to make it be near 1. So the discriminator would like to reject these samples as being fake, while the generator would like to fool the discriminator into thinking that they're real. You can think of the generator and the discriminator as being a little bit like counterfeiters and police. The counterfeiters are trying to make money that looks realistic, and the police are trying to correctly identify counterfeit money and reject it without accidentally rejecting real money. As the two adversaries are forced to compete against each other, the counterfeiters must become better and better if they want to fool the police. And eventually, they're forced to make counterfeit money that is identical to real money. Similarly, in this framework, the generator must eventually learn to make samples that come from the distribution that generated the data. So let's look at the generator network in a little bit more detail. We can think of the generator network as being a very simple graphical model shown on the left. There's a vector of latent variable z, and there's a vector of observed variables x. And depending on the model architecture, we usually have every member of x depend on every layer of z. So every member of x depend on every member of z. So I've drawn this as just a simple vector-valued model where we see one edge. You could also imagine expanding it into a graph of scalar variables, where it would be a bipartite directed graph. The main reason that generative adversarial networks are relatively simple to train is that we never actually try to infer the probability distribution over z given x. Instead, we sample values of z from the prior, and then we sample values of x from p of x given z. Because that's ancestral sampling in a directed graphical model, it's very efficient. In particular, we accomplish this ancestral sampling by applying the function g to the input variable z. One of the very nice things about the generative adversarial networks framework is that there are not really any requirements other than differentiability on g. Unlike nonlinear ICA, there is no requirement that z have the same dimension as x, for example. Or Boltzmann machines require energy functions that are tractable and have different tractable conditional distributions. We don't actually need to be careful to design values that have multiple different conditionals that are all tractable in this case. We only really need to make one conditional distribution tractable. There are a few properties that we'd like to be able to guarantee that impose a few extra requirements on G. In particular, if we want to be sure that we're able to recover the training distribution, we need to make sure that X has a higher dimension than Z, or at least an equal dimension. This is just to make sure that we aren't forced to represent only a low-dimensional manifold within X space. An interesting thing is that it's actually possible to train the generator network even if we don't provide support across all of X space. If we make Z be lower dimensional than X, then we obtain a low-dimensional manifold that assigns no probability whatsoever to most points in X space. But we're still able to train the model using the discriminator as a guide. That's kind of an unusual quirk that sets this framework apart from the methods that are based on maximizing a density function. Those would break if we evaluated the logarithm of zero density. So the training procedure is to choose an optimization algorithm. You can pick your favorite one. I usually like to use Atom these days. And then repeatedly sample two different mini batches of data. One of these is a mini batch of training examples that you draw from the data set, and the other mini batch is a set of input values Z that we sample from the prior and then feed to the generator. We then run gradient descent on both of the players' costs simultaneously. In one optional variant, we can also run the update for the discriminator more often than we run the update for the generator. I personally usually just use one update for each player. Each player has its own cost, and the choice of the cost determines exactly how the training algorithm proceeds. There are many different ways of specifying the cost. The simplest one is to use a minimax game, where we have a cost function j superscript d defining the cost for the generator, or for the discriminator, and then the cost for the generator is just the negative of the cost for the discriminator. So you can think of this as having a single value that the discriminator is trying to maximize and the generator is trying to minimize. So what exactly is this value that the two players are fighting over? It's simply the cross entropy between the discriminator's predictions and the correct labels in the binary classification task of discriminating real data from fake data. So we have one term where we're feeding data and where the discriminator is trying to maximize the log probability of assigning 1 to the data. And then we have another term where the discriminator is aiming to maximize the log probability of assigning 0 to the fake samples. When we look for an equilibrium point to a game, it's different than minimizing a function. We're actually looking for a saddle point of j superscript d. And if we're able to successfully find this saddle point, the whole procedure resembles minimizing the Jensen-Shannon divergence between the data and the distribution represented by the model. So as our first exercise, which will be accompanied by a little 5-minute break, we're going to study what the discriminator does when the discriminator plays this game. At the top of the slide, I've shown the cost function that the discriminator is going to minimize. And the exercise is to determine what the solution to d of x is, written in terms of the data distribution and the generator distribution. You'll also find that you need to make a few assumptions in order to make a clean solution to this exercise. So I'll give you about 5 minutes to work on this exercise, or if you don't want to do the exercise, feel free to talk with your neighbors or just take a break for a minute so that you don't need to remain attentive for too many consecutive minutes. I'm also happy to take questions from the mic during this time, if anyone's interested. Yeah, over there.
Yeah. My question is, what prevents the generator from always generating the same image? You see what I mean? It could just lazily learn to always generate one single realistic image and be fine with this.
Yeah, that's a good question. And it's an important part of ongoing research in generative adversarial networks. Essentially, if we're able to correctly play this minimax game, then the generator is not able to consistently fool the discriminator by always generating the same sample. The discriminator would learn to recognize that individual sample and reject it as being fake. In practice, it's difficult to find a true equilibrium point of this game, and one of the failure modes is actually to generate samples that have too little diversity to them. And because of that, we're having to study ways to improve our ability to find the equilibrium point of a game.
Thanks.
Hi.
Yeah.
Over here. Okay, so I'm on your left, actually, Ian.
Oh.
Here, I'm raising my hand. Okay, so I'm actually learning a bit of GANs as well and variational autoencoders, and I see certain resemblances in terms of sampling in this Z space. In what case should I, when generating samples, use GANs, and in what cases should I use variational autoencoders? Thanks.
If your goal is to obtain a high likelihood, then you would be better off using a variational autoencoder. If your goal is to obtain realistic samples, then you would usually be better off using a generative adversarial network rather than a variational autoencoder. You can kind of see this in the cost function. The generative adversarial network is designed to fool the discriminator into thinking that its samples are realistic. And the variational autoencoder is designed to maximize the likelihood.
Hi. How to sample from the data? Is just uniform distribution or?
That's also a really good question, and I think one that is a topic of ongoing research. The naive way of implementing the algorithm, and the one that everyone does so far, is to sample uniformly from the training data, and also to sample uniformly from the Z space. But you could imagine that importance sampling could give us big improvements. In particular, most of the points that we train the generator on are wasted because we're usually going to sample from points that are doing pretty well. And what we'd really like to do is find points that are doing very badly, or maybe points that lie on the boundary between two modes in order to adjust those boundaries. So you could imagine that as a procedure for doing importance sampling where we visit latent codes that yield more important aspects of the learning process, and then reweight those samples to correct for the bias in the sampling procedure could actually lead to an improvement.
So I just have one quick question. I'm surprised, well, extremely impressed by this beautiful algorithm. But one thing that I'm rather confused by is why don't strange artifacts appear on the representation for the created by the generator? And once it's created by the generator, it has some any sort of non-visually relevant artifact, whether it is a non-smoothness, and then that would just mean the discriminator is set up to just win. Does that make sense?
Yeah, that makes sense. So there are unusual artifacts that appear in samples created by the generator. And in a lot of cases, we're fortunate that those artifacts are somewhat compatible with the blind spots in the discriminator. One example is if we use a convolutional generator, the generator is somewhat inclined to producing unusual tile patterns. There's a really good blog post by Agustus Odina, Vincent Dumoulin, and Chris Ola. I'm sorry if I forgot any of the authors in that list, about the checkerboard patterns that appear when you use deconvolution with large stride in the generator. And then the good news is that the discriminator is also using convolution, presumably with similar stride. And so it might actually become blind to the same grid patterns that the generator creates.
That's the best answer. For exactly what he's right.
But more generally, there are a lot of artifacts that come out of the generator that don't really seem all that relevant to the sample creation process, and the discriminator spends a lot of its time learning to reject patterns that ideally it would just not ever have to encounter in the first place. Like on MNIST, which is a very simple data set with just handwritten digits on a background, if you look at the weights that the discriminator learns in the first layer, they often look a little bit like Fourier bases. So early on in learning, they're realizing that the generator often makes a lot of high frequency stuff, and the data doesn't really have that frequency. And so the discriminator is looking at this whole spectrum of different frequencies in order to figure out if there's too much of different bands present or not. And really, it seems like it would be much better for the generator to go straight to making pen strokes and the discriminator to go straight to paying attention to pen strokes instead of spending all of its time policing exactly how sharp the transitions between neighboring pixels are. Yep.
So if just trying to understand this objective function a little bit better, if you fix the generator so that it just does negative sampling, or rather, let me ask, what is the relation between this objective function and a negative sampling approach, the kind that are used with like word to vec?
Oh, negative sampling for word to vec. I haven't really thought about that. One connection to negative sampling is when training Boltzmann machines, we generate samples from the model in order to estimate the gradient on the log partition function, and we call that the negative phase. You can think of the generative adversarial network training procedure as being almost entirely negative phase. The generator only really learns from the samples it makes. And it makes it a little bit like when you carve a statue out of marble, you only ever remove things rather than adding things. It's kind of a unique peculiarity of this particular training process. So in the interest of time, I think I should move on to the solution to this exercise, but I'll continue taking more questions, probably most of them at the next exercise break. You think I should take one more? Or? Okay. Yeah, okay, so yeah, I'll take your question next when I come to exercise 2. So the solution to exercise 1, and as you recall, if you were paying attention to the questions rather than to the exercise, we're looking for the optimal discriminator function d of x in terms of p data and p generator. To solve this, it's best to assume that both p data and p generator are non-zero everywhere. If we don't make that assumption, then there's this issue that some points in the discriminator, the discriminator's input space might never be sampled during its training process, and then those particular inputs would not really have a defined behavior because they're just never trained. But if we make those relatively weak assumptions, we can then just solve for the functional derivatives, where we regard d of x as being almost like this infinite dimensional vector, where every x value indexes a different member of the vector, and we're just solving for a big vector like we're used to doing with calculus. So in this case, we take the derivative with respect to a particular d of x output value of the cost function, and we set it equal to 0. It's pretty straightforward to take those derivatives, and then from there it's straightforward algebra to solve this stationarity condition. And what we get is that the optimal discrimination function is the ratio between p data of x and the sum of p data of x and p model of x. So this is the main mathematical technique that sets generative adversarial networks apart from the other models that I described in the family tree. Some of them use techniques like lower bounds, some of them use techniques like Markov chains. Generative adversarial networks use supervised learning to estimate a ratio of densities. And essentially, this is the property that makes them really unique. Supervised learning is able to, in the ideal limit of infinite data and perfect optimization, it's able to recover exactly the function that we want. And the way that it breaks down is different from the other approximations. It can suffer from underfitting if the optimizer is not perfect, and it can suffer from overfitting if the training data is limited and it doesn't learn to generalize very well from that training data. So far, I've described everything in terms of a minimax game, where there's a single value function and one player tries to maximize it and the other player tries to minimize it. We can actually make the game a little bit more complicated, where each player has its own independently parameterized cost. So in all the different versions of the game, we pretty much always want the discriminator to be using the original version of the game, where it's just trying to be a good binary classifier. But there are many different things we might consider doing with the generator. In particular, one really big problem with the minimax game is that when the discriminator becomes too smart, the gradient for the generator goes away. One of the really nice properties of the cross-entropy loss function that we use to train sigmoid classifiers and softmax classifiers is that whenever the classifier is making a mistake, whenever it's choosing the wrong class, the gradient is guaranteed to be non-zero. The gradient of the cross-entropy with respect to the logits approaches 1 as the probability assigned to the correct class approaches 0. So we can never get in a situation where the classifier is unable to learn due to a lack of gradient. Either it has gradient and it's making a mistake, or it lacks gradient and it's perfect. So the discriminator has this particular property, but unfortunately, if we negate the discriminator's cost, then the generator has the opposite of that property. Whenever the generator is failing to fool the discriminator completely, then it has no gradient because the output of the discriminator has saturated. What we can do is, instead of flipping the sign of the discriminator's cost, we can flip the order of the arguments to the cross-entropy function. Specifically, this means that rather than trying to minimize the log probability of the correct answer, we have the generator try to maximize the log probability of the wrong answer. Both of these cost functions are monotonically decreasing in the same direction, but they're steep in different places. At this point, it's no longer possible to describe the equilibrium with just a single loss function. And the motivations for this particular cost are far more heuristic. We don't have a good theoretical argument that this places the Nash equilibrium in the right place. But in practice, we see that this cost function behaves similar to the minimax cost function early in learning. And then later in learning, when the minimax function would start to have trouble with saturation and a lack of gradient, this cost function continues to learn rapidly. So this is the default cost function that I usually advocate that most people use, even though it's not quite as theoretically appealing. Generative adversarial networks did not really scale to very large inputs when my co-authors and I first developed them. And eventually they were scaled to large images using a hand-designed process called lap GANs that use a Laplacian pyramid to separate the image into multiple scales and generate each scale independently. But more recently, the way that they are usually used is following an architecture that was introduced in a collaboration between a startup called Indico and Facebook AI Research. And this architecture is called the DC GAN architecture for deep convolutional generative adversarial networks. Even in the original paper, generative adversarial networks were deep and convolutional, but this paper placed greater emphasis on having multiple convolutional layers and using techniques that were invented after the original development of generative adversarial networks, such as batch normalization. So in particular, when we generate images, we might wonder exactly what we should do to increase the resolution as we move through a convolutional network. The answer from the DC GAN architecture is just to use a stride of greater than 1 when using the deconvolution operator. Another important contribution of the DC GAN paper is to show that it's important to use batch normalization at every layer except for the last layer of the generator network. That makes the learning process much more stable. And since then, GANs have been applied to a wide range of large image generation tasks. DC GANs showed that you can generate really good images of bedrooms. In particular, many different data sets that have a small number of output modes work really well with DC GAN style architectures. So here we can see that we're getting realistic beds, blankets, windows, cabinets, and so on. And that we have quite a variety of different kinds of lighting. And all the different sources of lighting are rendered in a very nice, realistic way. Another domain where generative adversarial networks work well, because the number of outputs is restricted, is the domain of images of faces. DC GANs were shown to work very well on faces, and in particular, they showed that the latent code is actually very useful for representing faces. Many of you have probably seen the result that language models that have word embeddings can have properties where the word embedding for queen, if you subtract the word embedding for female and add the word embedding for male, gives a word embedding very close to the word embedding for king. So you can actually do algebra in latent space and have it correspond to semantics. The authors of the DC GAN paper showed that generative adversarial networks provide a similar property for images. In particular, if we take the the image embedding for images of a man with glasses and subtract the embedding for images of a man and add the embedding for images of a woman, we obtain the embedding that corresponds to images of women with glasses. All of the images in this slide were generated by the network. None of them are training data. They all come from decoding different embeddings. So this shows that we're able to do algebra in latent space and have that algebra correspond to semantic properties, just like with language models. But what's even more exciting than language models is that we're actually able to decode this latent variable to a rich high-dimensional image where all the different thousands of pixels are actually arranged correctly in relation to each other. In the case of language models, we only had to find an embedding that was really close to the embedding for the word king. But we didn't have to actually map from that embedding to some kind of complicated data space. So here we've shown we can go one step further and actually accomplish that mapping task. When we try to understand exactly how generative adversarial networks work, one thing that's important to think about is whether the particular choice of divergence that we minimize is really important. And in the past, I and several other people have argued that generative adversarial networks made good samples and obtained bad likelihood because of the divergence that we chose. But I no longer believe that, and I'm going to give you an argument now that the divergence doesn't matter, but I will start by explaining to you why you might think that it should. So if we maximize the likelihood of the data, that's similar to, that's equivalent to minimizing the KL divergence between the data distribution and the model distribution. And that's shown on the left in this panel here. The data distribution is represented by the blue curves, where we have a bimodal data distribution for this example. The model distribution is represented by the dashed green curve. And in this particular demonstration, I'm assuming that the model is a Gaussian with a single mode, so it's not able to represent the data distribution correctly. So this is what the maximum likelihood solution to this problem would give us. The Gaussian ends up averaging out the two different modes. The KL divergence is not actually symmetric. Maximum likelihood corresponds to minimizing the KL divergence with the data on the left and the model on the right. But we can actually flip that around. We can minimize the KL divergence with the model on the left and the data on the right. And when we do that, we get a different result, where instead of averaging out the two modes, the model, as shown in the panel on the right here, will choose one of the modes. We can think of KL data comma model as saying that the model should put probability mass everywhere that the data puts probability mass. And we can think of KL model comma data as saying that the model should not put probability mass anywhere that the data does not put probability mass. In the left, it's really important to have some mass on both peaks. On the right, it's really important to never generate a sample in the valley between the two peaks, because none of the data ever actually occurs there. Both of these are perfectly legitimate approaches to generative modeling, and you can choose one or the other based on whichever task you are using and what the design requirements for that task are. The loss that we traditionally use with generative adversarial networks, mostly because it was the thing that popped into my head in a bar, as Aaron mentioned, is pretty similar to the divergence on the right. But since that night in the bar, I've realized that it's possible to use other divergences, and several papers by other people have been published on how to use other divergences. And I now no longer think that the choice of divergence explains why we get really good samples and don't get as good of likelihood. So here's how you can actually get maximum likelihood out of a generative adversarial network, where you approximately minimize the KL divergence between data and model rather than model and data. For the discriminator network, you use the same cost function as before, which is just the binary classification task. And for the generator network, we now sample from the generator, and then we penalize it according to e to the value of the logits of the discriminator. And if the discriminator is optimal, this has the same expected gradient with respect to the parameters as the KL divergence data in the model does. So it's approximating maximum likelihood by using supervised learning to estimate a ratio that would be intractable if we were to evaluate the maximum likelihood criterion directly. In general, we can think of these different costs as being like reward functions. We can kind of think of the generator net as being a reinforcement learning agent, where it takes actions and we reward its actions depending on the way that the environment responds. The thing that makes this particular reinforcement learning setup a little unusual is that part of the environment is another learning agent, in particular the discriminator. All these different costs have one thing in common. You can compute the cost using only the output of the discriminator. And then for every sample, you just give a reward that depends on exactly what the discriminator did. So if we look at a graph of the cost that the generator incurs as a function of the output of the discriminator, we can see that all these different costs increase as we move from left to right. And decrease as we move from left to right. Essentially, that's saying that if you make the discriminator think that the samples that the generator created are real, then you incur a very low cost. We can see the way that they saturate in different places, and also we can see how sampling along these curves would give us very different variance in the estimate of the gradient. The green curve that lies the highest is the heuristically motivated cost, which is designed not to saturate when the generator is making a mistake. So if you look at the very extreme left, where the discriminator is outputting zeros, where the discriminator is successfully rejecting the generator samples, this cost function has a high derivative value. So the model is able to learn rapidly early on when its samples did not yet look realistic. Then if we move downward in the series of plots, the blue curve, the minimax curve, is the one that we originally used to design this model framework, and the one that's the easiest to analyze using the minimax theorem. This curve is relatively flat most of the way across and starts to curve down gently as the samples become more realistic. And then finally, the maximum likelihood cost, which has the negation of an exponential function in it, is very flat on the left side, but then shoots off exponentially downward as we get very far to the right. So we can see that we would actually incur very high variance in the estimate of the gradient if we were to use that particular function, because almost all the gradient comes from a single member of the mini-batch, whichever one is the most realistic. And because of that, we don't usually use the maximum likelihood cost with generative adversarial networks. We use one of the other costs that has nicer saturation properties and nicer variance properties, but it is a perfectly legitimate cost. And when we go ahead and we use that cost to train, there's a few other ways of approximating the KL divergence, but none of the different ways of approximating the KL divergence give us blurry samples like we get with a VAE. So we used to think that the VAE was using the KL divergence and got blurry samples, and GANs were using the reverse KL divergence and got sharp samples. But now that we're able to do both divergences with GANs, we see that we get sharp samples both ways. My interpretation of this is that it is the approximation strategy of using supervised learning to estimate the density ratio that leads to the samples being very sharp, and that something about the variational bound is what leads to the samples for the VAE being blurry. And there's one other possibility, which is that the model architectures we use for generative adversarial nets are usually a little bit different. VAEs usually are conditionally Gaussian and usually have an isotropic Gaussian at the output layer. Generative adversarial networks don't need to have any particular conditional distribution that you can evaluate. So the last layer is often just a linear layer, which would look kind of like a Gaussian distribution with a complete covariance matrix instead of a restricted covariance matrix. So it's possible that that complete covariance matrix at the last layer removes some of the blurriness. But we no longer think that the choice of the divergence is really important to understanding how generative adversarial networks behave. Earlier, I showed you a family tree of different generative models, and I said we were going to pretend that all of them do maximum likelihood. And clearly, they don't actually do that. Now that we've seen how generative adversarial networks work in a little bit more detail, we can actually start to describe exactly how it is that they compare to some of the more similar generative models. In particular, noise contrastive estimation is a procedure for fitting many different generative models, including Boltzmann machines and other different types of generator nets. And noise contrastive estimation uses exactly the same value function that we use as the value function for the minimax game for generative adversarial nets. So a lot of people look at this and think maybe these two methods are almost the same thing. And I myself wondered about that for a little while. So it turns out that actually this same value function also appears for maximum likelihood if you look at it the right way. So what this value function consists of is on the left, we have a term where we sample values from the data and we measure the log discriminator function. On the right, we sample values from a generator function and we measure the log of 1 minus the discriminator function. It turns out that the differences between noise contrastive estimation, maximum likelihood estimation, and generative adversarial nets all revolve around exactly what the generator and the discriminator and the learning process are. So for generative adversarial networks, the discriminator is just a neural network that we parameterize directly. The function d of x is just directly implemented. For both noise contrastive estimation and maximum likelihood estimation, the discriminator is a ratio between the model that we're learning and the sum of the model density and the generator density. So that probably got a little bit confusing right there. What is this model that we are learning and how is it different from the generator? Well, it turns out that for noise contrastive estimation, the generator is used as a source of reference noise, and the model learns to tell samples apart from noise by assigning higher density to the data. So noise contrastive estimation might consist of generating samples from a Gaussian distribution and then training this discriminator function to tell whether a given input comes from the Gaussian distribution or comes from the data distribution. And it implements that discriminator function by actually implementing an explicit tractable density over the data and by accessing an explicit tractable density over the generator that creates the noise.
Can I ask a question?
Yeah, go ahead.
Because you have this nice slide there. My name is Jürgen Schmidhuber from the Swiss AI Lab, and I was wondering whether you can relate these very interesting GANs or GANs to the other adversarial network that we had back then in 1992, where you had two types of network fighting each other, also playing a minimax game, where one of them tried to try to minimize an error function that the others were maximizing. And it was not exactly like that, but it was very similar in many ways, because there you had an image coming in, and then you had these code layers, like in an autoencoder, and then you try to find a representation, initially a random representation of the image, but then for each of these units in the code layer, there was a predictor which tried to predict this code unit from the other guys in the code layer, and then the predictors try to minimize the error, just like the feature detectors, the code units, try to maximize it, trying to become as unpredictable as possible. Now, this is closely related to coming up with this reference noise vector that you just mentioned, because of course then in the code layer you basically get, in the ideal case, a factorial code where each of these units is statistically independent of each other, of the other units, but still it tells you a lot about the image. So you still can attach an autoencoder to that and then get a generative distribution. You just wake up the code layer units and you randomly activate them according to their probabilities. They are factorial code, which means that you get then images that are just reflecting the original distribution of the images. So in many ways very similar, but in other ways different. And I was wondering whether you have comments on the similarities and differences of these old adversarial networks.
Yeah, so Jürgen has asked me if I have any comment on the similarities and differences here, but he's in fact aware of my opinion because we've corresponded about this by email before, and I don't exactly appreciate the public confrontation. If you want to form your own If you want to form your own opinion about whether predictability minimization is the same thing as generative adversarial networks, you're welcome to read the paper. One of the NIPS reviewers requested that we add a description of predictability minimization to the generative adversarial networks paper, and we indeed added our comments on the extent to which we think that they are similar, which is that they are not particularly similar to the NIPS final copy.
Just for completeness, however, so I reacted to exactly these changes, and then you did not comment. It's not true that you commented or reacted to these confrontations. Yeah. So there are comments which you did not address, and I still think
we've had a very extensive email thread, and I would prefer to use my tutorial to teach about generative adversarial networks. If people want to read about predictability minimization, please do so.
Yeah. Just always make sure you have the related work section.
The comments have been added to the NIPS paper. So returning to the comparison to noise contrastive estimation, which is far more similar to generative adversarial networks than predictability minimization in that they have exactly the same value function. We find that for noise contrastive estimation, the learning of the final generative model occurs in the discriminator. And for the generative adversarial network, the learning occurs in the generator. That's one way that they're different from each other, and it has consequences on exactly what they are able to do. An interesting thing is that maximum likelihood estimation also turns out to use this same value function and can also be interpreted as having a discriminator function inside it. The difference between noise contrastive estimation and maximum likelihood estimation is that for noise contrastive estimation, the noise distribution is fixed and never changes throughout training. If we choose to use a noise distribution that is Gaussian as the reference distribution, then in practice, learning tends to slow down relatively quickly once the model has learned to create samples that are easily distinguishable from a Gaussian. In maximum likelihood estimation, we take the parameters of the model distribution and we copy them into the noise distribution. And we do this before each step begins. So in some ways, the maximum likelihood estimation procedure can be seen as the model constantly trying to learn its own shortcomings and distinguish its own samples from the data. In the generative adversarial networks approach, we constantly update the generator network by following the gradient on its parameters. All three of these approaches constantly follow the gradient on the parameters of the discriminator. So we can see the way that we get some computational savings relative to maximum likelihood by looking at the corners that both noise contrastive estimation and generative adversarial networks cut. For noise contrastive estimation, it's clear that the main corner we cut is that we never update the noise distribution, and that eliminates a lot of computations right there. For generative adversarial networks, the way that we're able to cut a corner is that we don't need to make sure that there's an exact correspondence between a density and a sampler. So for maximum likelihood, we need to be able to sample, if we're going to follow this particular implementation of maximum likelihood. We need to be able to sample from the model when we evaluate the term on the right, but we also need to be able to evaluate densities of the model in order to evaluate the D function. And we need to perform computations that convert between this density representation and the sampling procedure. Generative adversarial networks only ever sample from G and only ever evaluate D. There's no need to perform these transitions from densities to sampling procedures. And that provides a lot of computational savings. So I've completed this section of our roadmap on exactly how it is that generative adversarial networks are able to work from a theoretical point of view. And now I'll move on to a few tips and tricks that should help you to make them work better in your own practical applied work. The first really big tip is that labels turn out to really improve the subjective sample quality a lot. As far as I know, this is first observed by Emily Denton and her collaborators at NYU and Facebook AI Research, where they showed that back when generative adversarial networks didn't work very well at all, you could actually get them to work really well if you made them class conditional. So Mehdi Mirza and Simon Osendero had developed a conditional version of the generative adversarial network, where you could give some input value that should control what output should come out. And Emily and the collaborators showed that if you used a class label as the input, you could then create an output value of an image from that class, and that these images would be much better than if you just learned the density over images to begin with. Another thing is that even if you don't want to go fully to the level that you have a class conditional model, you can learn a joint distribution over the probability distribution of x and y. And even if at sample time you don't provide an input y to request a specific kind of sample, the samples that come out will be better. Tim Solomons and I did this in our paper that we'll be showing at the poster session tonight. It's not a key contribution of our paper, but it's one of the tricks that we use to get better images. One of the caveats about using this trick is that you need to keep in mind that there are now 3 different categories of models that shouldn't be directly compared to each other. There are those models that are trained entirely without labels, there are models that are class conditional, and there are models that are not class conditional but that benefited from the use of labels to guide the training somewhat. And it wouldn't really be fair to make a class conditional model and then say that it's strictly superior to some model that didn't use labels to improve its samples at all. Another tip that can really help a lot is a technique that I call one-sided label smoothing. And we also introduced this in the paper with Tim that we're showing tonight. The basic idea of one-sided label smoothing is that usually when you train the discriminator, you're training it to output hard ones on the data and hard zeros on the fake samples. But it's much better if you train it to output a soft value like 0.9 on the data. And on the fake samples, it should still strive to output zeros. That's why it's called one-sided, is that we only smooth the side that's on the data. So what this will do is you can think of it as introducing some kind of like a leak probability that sometimes the data has been mislabeled, that we accidentally gave you something fake and said it was real. In particular, this will reduce the confidence of the model somewhat so that it will not predict really extreme values. It's important not to smooth the generator samples, and we can see this by optimizing what the optimal discriminator is. If we smooth by replacing the positive targets with 1 minus alpha and replacing the negative targets with beta, then we see that we get this ratio of densities again, where in the numerator we have 1 minus alpha times the data distribution, and we have beta times the model distribution. Because this value in the numerator determines where the output of the discriminator function is large, and therefore determines where the generator wants to steer samples, we need to make sure that this second term does not appear in the numerator. Otherwise, we would reinforce the current behavior of the generator. If the generator is making lots of weird pictures of grids, and we assign beta times p model to those weird pictures of grids in the discriminator, we will just ask it to keep making weird pictures of grids forever. And the gradient near those images will not steer you away from them. So that's why we always set beta to 0 and only really smooth using the alpha term on the left term. So we didn't invent label smoothing, we just advocated the one-sided use of it for the discriminator. Label smoothing dates back to the 1980s. I'm not sure where it originated. Christian Szegedy and his collaborators showed that it works really well for regularizing inception models. And one of the really nice properties that I've observed for it is that compared to weight decay actually will reduce the training accuracy of your model. It will actually cause the model to make classification mistakes by shrinking the weights until it's not possible to make the correct classification anymore if you turn up the weight decay coefficient high enough. Label smoothing will not actually introduce mistakes. It will just reduce the confidence of the correct classifications, but it will never actually steer the model toward an incorrect classification. So for generative adversarial networks, this allows the discriminator to still more or less know which direction is real data and which direction is fake data, but it doesn't actually result in it misguiding the generator. And it gets rid of really large gradients. It gets rid of behaviors where the discriminator linearly extrapolates to decide that if you move a little bit in one direction, then moving very far in that direction will give you more and more realistic samples. It's important to use batch normalization at most layers of the model. And I won't go into batch normalization in detail, but the idea is you take a full batch of input samples and you normalize the features of the network by subtracting the mean of those features across the whole batch and dividing by their standard deviation. This makes the learning process a lot better conditioned. Unfortunately, the use of these normalization constants that are computed across a whole mini-batch can induce correlations between different samples generated in the same mini-batch. So I'm showing you a grid of 16 examples in the top image that were all in one batch, and then the next grid of 16 samples is all in another batch. Same generator model in both cases. The only reason that there seems to be a common theme in all the examples in each image is that they're using the same mean and standard deviation normalizing constants. And in this case, the model has kind of pathologically learned to have its output depend a lot more on the precise randomly sampled value of that mean and that standard deviation, rather than paying attention to the individual values in the code. So in the top, we see a lot of very orange images, and in the bottom, we see a lot of very green images. So to fix that problem, we are able to change to different versions of batch normalization that actually process every example in the same way. And the simplest of these is what we call reference batch normalization, where you just pick a reference batch of examples at the start of training and you never change them. And you always compute the mean and the standard deviation of the features on those reference images. And then you use them to normalize different images that you train on. It means that every image throughout all of training is normalized using the statistics from the same reference batch. And there's no longer this random jitter as we resample the images that are used to create the normalizing statistics. Unfortunately, because we always use the same images, we can start to overfit to that particular reference batch. To partially resolve that, we introduced a technique called virtual batch normalization. And the basic idea here is that every time we want to normalize an example X, we normalize it using statistics computed both on the reference batch and on the example X itself added to that batch. A lot of people ask me questions about how to balance the generator and the discriminator, and if they need to be carefully adjusted to make sure that neither one of them wins. In reality, I usually find that the discriminator wins, and I also believe that this is a good thing. The way that the theory works is all based on assuming that the discriminator will converge to its optimal distribution, where it correctly estimates the ratios that we're interested in. And we really want the discriminator to do a good job of that. In some cases, you can get problems where if the discriminator gets really good at rejecting generator samples, the generator doesn't have a gradient anymore. Some people have an instinct to fix that problem by making the discriminator less powerful. But I think that's the wrong way of going about it. I think the right way to do it is to use things like one-sided label smoothing to reduce the how extreme the gradients from the discriminator are, and also to use things like the heuristic non-saturating cost instead of the minimax cost. And that will make sure that you can still get a learning signal, even when the discriminator is able to reject most of the samples. There are a few other things that you can do to try to make sure that the coordination between the generator and the discriminator works out correctly. In particular, we really want the discriminator to always do a good job of estimating that ratio. We want the discriminator to be really up to date and to have fit really well to the latest changes to the generator. That motivates running the update on the discriminator more often than the update on the generator. Some people still do this. I don't usually find that it works that well in practice. I can't really explain why it doesn't work very well. All the theory suggests that it should be the right thing to do. But that particular approach doesn't seem to consistently yield an obvious payoff. We're now coming to the most exciting part of the roadmap, which is the research frontiers in generative adversarial networks. Can I get a quick check on how much time I have left? Yes. So the biggest research frontier in generative adversarial networks is confronting the non-convergence problem. Usually when we train deep models, we are minimizing a cost function. And so we're using an optimization algorithm to perform minimization. There are a lot of things that can go wrong with minimization, especially when you're training a deep model. You can approach a saddle point rather than approaching a minimum. You can approach a local minimum rather than a global minimum. We're starting to become skeptical that local minima are as much of a problem as we used to think they were. And you can have all kinds of things with, like bad conditioning, high variance in the gradient, and so on. But for the most part, you're pretty much going to go downhill until eventually you stop somewhere, unless your hyperparameters are really bad. And you don't usually need to worry that your optimization algorithm will fail to even converge. In the case of looking for an equilibrium to a game, it is actually pretty difficult to guarantee that you will eventually converge to a specific equilibrium point, or even that you will stop in some particular location that isn't a great equilibrium. So to start looking at exactly how this works, we're going to do another exercise where we're going to analyze a minimax game and see what gradient descent does. For this game, we have a scalar variable x and a scalar variable y, and we have a value function x times y. And basically, the one player controls x and would like to minimize this value function. The other player controls y and would like to maximize it. And the exercise is to figure out if this value function has an equilibrium anywhere. If so, where is that equilibrium? And then to look at the dynamics of gradient descent and analyze gradient descent as a continuous time process and just determine what the trajectory that gradient descent follows looks like on this particular problem. And I can take a few more questions while people work on this one.
Question.
Yeah.
Now you have GANs that generate really, really nice results and train on a lot of data. I think like there's the vegan work presented here that's trained on 27 terabytes of video. So the thing I'm wondering is, nobody has looked at all these videos. How can you know that the GAN is not generating near duplicates? Is there any theoretical motivation? Is it related to overfitting? And are people trying near duplicate search to see if it's just very good at compressing this data instead of generating?
Yeah, so duplicating a training example would actually definitely be a form of overfitting. It's not something that we really believe happens in generative adversarial networks. We don't have a strong theoretical guarantee that it doesn't happen. One thing I can point out is that the generator never actually gets to see a training example directly. It only gets to see the gradients coming from the discriminator. So the discriminator would need to perfectly memorize the training example and then communicate it into the generator via the gradient. Another thing is, because we have this problem with fitting games, finding the equilibria like people are analyzing in the exercise right now, we tend to underfit rather than overfit. I'd be really quite happy if we started to overfit consistently. But it's actually pretty difficult to really measure how much we're overfitting, because you wouldn't really expect the model to perfectly copy a training example. It's more likely that it would mostly copy the training example and then kind of change a few small things about it. And we do things like look for nearest neighbors. We generate samples and then see what the most similar training example in terms of Euclidean distance is. But it's really easy to make a small change that causes a gigantic difference in Euclidean distance, so that can be kind of hard to tell if it's actually eliminating the duplicates or not. It's also worth mentioning that in many cases, generative adversarial nets aren't even necessarily compressing the data. Sometimes we actually train them with more parameters than there are floating point values in the original data set. We're converting it into a form where we can get infinitely many samples in a computationally efficient way. But yeah, we are usually compressing, as you said. Yeah.
Okay, and so my question is, right now in, like, for example, the vanilla GANs, right? You're taking noise, you're doing like a noise shaping in a sense, right? And then you're reconstructing some signals, some image in its native space, in like native basis. So my question is, what do you think of actually doing the generation in a more, say, sparsified basis of those types of signals? For example, maybe a cosine basis, or maybe even the coefficients of some dictionary. Do you think that it might make the learning of the GANs easier, or do you think it might not matter, or something like that? So I was just curious about
Oh, you're saying like should the output of the generator network be a set of bases.
Yeah, or for example, the coefficients of some, say natural basis, maybe a Fourier basis or some wavelet basis or a dictionary or something. Just wondering if that makes any difference to the learning, if it makes it easier, because you can maybe put some more priors on these bases, right?
So as a member of the deep learning cult, I'm not allowed to hand engineer anything. So, but the closest thing I've done to what you're suggesting is my co-author Bing Xu on the original generative adversarial net paper was able to train a really good generator net on the Toronto Faces dataset by doing layer-wise pre-training. I wasn't able to get the deep jointly trained model to fit that dataset very well back then. My guess is it would probably work now that we have batch norm. We didn't have batch norm back then. You can view what Bing did as being a little bit like what you're suggesting, because when you train the output layer of the generator in the pre-training step, it learns essentially a dictionary that looks a little bit like wavelet dictionaries. And then when you start training the deeper layers of the generator, those layers are essentially learning to output wavelet coefficients. And so I do think that would help, yeah.
Question. I can use after the GANs are trained to create more synthetic data set for another classifier, like the idea that after the GANs are trained, I kind of capture the probability distribution of my input and use them to automatically generate more images, like to avoid like how we normally use data set augmentation to jitter the images and stuff like that.
Yeah. So my former intern, Tianqi Chen, who was my intern when I was at Google, I don't want to disclose his project, but I'll tell you that he's doing something cool related to that. And if you talk to him, he can decide whether he wants to disclose it or not. I don't think I'm giving away anything about what he's done by saying that. I've also had a lot of other people tell me that sometimes when they're evaluating a generator network to see how well it's doing, that one test they'll run is they will create a synthetic data set using the generator and then train a classifier on that new data set, then use it to classify the real test set. And if that classifier is able to classify the real test set, they take that as evidence that their generator was pretty good, if it could be used to make a fake training set. There are a few downsides to that procedure, like for example, if you were generating one mode way too often, but you were still generating all the other modes occasionally, your classifier might still be pretty good, even though your generative model is screwed up. But it does basically seem to work. So in the interest of time, I think I'll move on to the solution of the exercise, but there'll be one more exercise, so you'll get to ask a few more questions. So the solution to this exercise, which is, we're looking at the value function of x times y, where x and y are just scalars. There is actually an equilibrium point where x is 0 and y is 0. When they're both 0, each of them causes the gradient to go away on the other one. And then we can look at the gradient descent dynamics by analyzing it as a continuous time system. So if we actually evaluate the gradients, dx dt is negative y, and dy dt is positive x. The sign difference is because one of them is trying to minimize the value function and one of them is trying to maximize it. If we then go ahead and solve this differential equation to find the directions, I guess there's a lot of different ways of doing it depending on exactly which pattern matching technique you're most comfortable with. My particular approach is to differentiate the second equation with respect to t, and then I get that d squared y dt squared is negative y. So I recognize from that we're looking at a sinusoidal basis of solutions, and from that you can guess and check the corresponding coefficients, and we get that we have this circular orbit where the only real thing that changes exactly what the circle looks like is the initial conditions. So if you initialize right on the origin, you'll stay on the origin. But if you initialize off the origin, you never get any closer to it. So gradient descent goes into an orbit and oscillates forever rather than converging. And then this is continuous time gradient descent where we have an infinitesimal step size. If we use a larger step size, then it can actually spiral outward forever. So there are actually conditions that you can check to see whether or not simultaneous gradient descent will converge or not. And they involve complex eigenvalues of a matrix of second derivatives, and I won't go into it because it's not really the kind of thing that makes for a nice talk. But the long and short of it is that the generative adversarial nets game does not satisfy the main sufficient condition for convergence. So that doesn't mean that they don't converge. It means that we don't know whether they converge or not, according to the main criterion that we can look at. And it seems like in practice, they do converge sometimes and they don't other times. And we don't have a great understanding of why they do or don't. But the most important thing to understand is that simultaneous gradient descent is not really an algorithm for looking for equilibria of games. It sometimes does that, but it's not really its purpose. And the most important research direction in generative adversarial nets is to find an algorithm that does find equilibria in these high-dimensional, continuous, non-convex spaces. It's important to mention that if we were able to optimize the generative adversarial network in function space, if we were able to update the density function corresponding to the generator and the discriminator's beliefs about the generator directly, then we can actually use convexity in function space to prove that simultaneous gradient descent converges for that particular problem. The reason that this breaks down is that we don't actually update the densities directly. We update the G and D functions that do the sampling and the ratio estimation. And then on top of that, we represent G and D using parametric functions, deep neural networks, where the actual output values of G and D are very non-convex functions of the parameters. And so that causes us to lose all of our guarantees for convergence. The main way that we see this affect the generative adversarial networks game is that we get behaviors like oscillation, where the generator continually makes very different samples from one step to another, but doesn't ever actually converge to producing a nice consistent set of samples. In particular, the worst form of non-convergence, and one that happens particularly often, is what we call mode collapse, where the generator starts to make only one sample or one similar theme of related samples. It usually doesn't output exactly the same image over and over again, but it might do something like every image it creates is a picture of the same dog, and the dog is in different positions or has different objects in the background, or we might see, every sample it makes is a beach scene, for example. But it is essentially generating too few of things. So the reason that mode collapse happens particularly often for the generative adversarial nets game is that the game is a little bit pathological in the way that we specify the value function. In particular, if we look at the minimax version, the min-max and the max-min do different things. If we do the min-max, where we put the discriminator in the inner loop and maximize over it there, then we're guaranteed to converge to the correct distribution. In practice, we don't actually do the maximization in the inner loop. We do gradient descent on both players simultaneously. If we put G in the inner loop, that actually corresponds to a pathological version of the game where the generator learns to place all of its mass on the single point that the discriminator currently finds to be most likely. So Luc Metz and his collaborators produced a really nice visualization of this in their recent paper submitted to iClear, where we have this target distribution shown in the middle of the slide, which has several different modes in two-dimensional space. And then over time, we see how, as we move left to right and train a generative adversarial network, we learn to sample from different modes of that distribution, but we don't ever actually get multiple modes at the same time. This is because simultaneous gradient descent can sometimes behave a little bit like min-max and a little bit like max-min, and we're just unlucky enough that it often behaves more like max-min and does the thing that we don't want. Some people have explained mode collapse in terms of the fact that we use the reverse KL loss that I described earlier when I said that I don't believe the reverse KL loss describes why we get sharp samples. Because the reverse KL loss would prefer to choose a single mode rather than average out two different modes, it does superficially seem like it might explain why we get mode collapse. But I don't think that it is actually the explanation in this case. For one thing, if we use the forward KL, we still get mode collapse in many cases. Also, the reverse KL divergence does not say that we should collapse to a single mode. It says that if our model is not able to represent every mode and to put sharp divisions between them, then it should discard modes rather than blur modes. But it would still prefer to have as many modes as the model can represent. And with generative adversarial networks, what we usually see is a collapse to a much smaller number of modes than the model can represent. That makes me believe that the problem is really that we're doing max-min rather than that we're using the wrong cost. We often see that generative adversarial networks work best on tasks that are conditional, where we take an input and map it to some output, and we're reasonably happy with the result as long as the output looks acceptable. And in particular, we may not really notice if there's low diversity in the output. So for example, sentence to image generation, as long as we get an image that actually resembles the sentence, we're pretty happy with the output, even if there isn't that much diversity in it. Scott Reed and his collaborators have recently shown that for these sentence to image tasks, generative adversarial networks seem to produce samples that are much less diverse than those produced by other models. In the panel on the right, we can see how the sentence, "A man in an orange jacket with sunglasses and a hat skis down a hill," gives 3 different images of a man in essentially the same pose when we use a generative adversarial network. But using the model developed in this paper, it's possible to get greater diversity in the output. One way that we can try to reduce the mode collapse problem is to introduce what Tim Solomon calls mini-batch features. These are features that look at the entire mini-batch of samples when examining a single sample. If that sample is too close to the other members of the mini-batch, then it can be rejected as having collapsed to a single mode. This procedure led to much better image quality on CFAR10. We're now able to see all the different 10 classes of images in CFAR10. On the left, I show you the training data, so you can see that this data is not particularly beautiful to start with. It's 32 by 32 pixels, so it's relatively low resolution. You can see that there are things like cars, airplanes, horses, and so on. In the panel on the right, we have a GAN trained with mini-batch features, and it is now successfully able to generate many different recognizable classes like cars and horses and so on. Previous generative adversarial networks on CFAR10 would usually give only photo texture blobs that would look like regions of grass and regions of sky, regions of water, but would not usually have recognizable object classes in them. On ImageNet, the object classes are not as recognizable, but if we go through and cherry pick examples, we can see some relatively nice recognizable images where we get many different kinds of animals like dogs and maybe koalas and birds and so on. If we look at some of the problems that arise with this sampling procedure, we can see some of the amusing things that convolutional networks get wrong. One thing in particular is that I think probably due to the way that pooling works in the convolutional network, the network is usually testing whether some feature is absent or present, but not testing how many times it occurs. So we tend to get multiple heads in one image or animals that have more than one face on the same head. We also often get problems where the perspective of an image is greatly reduced. And I think this might be due to the network not having enough long-range connections between different pixels in the image, that it's hard for it to tell that things like foreshortening ought to happen. In particular, the picture of the gray and orange dog looks literally like a cubist painting to me, where the cubists intentionally remove the perspective. Some of them also just look like we've taken an animal and skinned it and laid its fur out flat on the ground and then taken an axis-aligned photo of it. We also see a lot of problems where individual details are great, but the global structure is wrong. Like there's this cow that is both quadrupedal and bipedal. There's a dog whose eyes are different sizes from each other, and a cat that has like a lamprey mouth. We also often just see animals that don't really seem to have legs, that they just sort of vanish into fur blobs that often conveniently end at the edge of the image so that the network doesn't need to provide the legs. So did anybody notice anything that actually looked real in these samples? Aaron? Yeah, so the cat was real to test your discriminator network. Good job, Aaron. Another really promising way to reduce the mode collapse problem besides mini-batch features is called unrolled GANs. This was recently introduced by Google Brain and was submitted to iClear. And I guess it's worth mentioning that a few other people had suggested doing this for a few years beforehand. So it is an idea that was floating around in the ether a little bit. I imagine some people in the audience are probably thinking like, oh, I told people about that. But Brain was the first to go ahead and get it to really work really well. Revisiting the same visualization that we saw earlier, their unrolled GAN is able to actually get all the different modes. So the way that unrolling works is that to really make sure that we're doing min-max rather than max-min, we actually use that maximization operation in the inner loop as part of the computational graph that we backprop through. So instead of having a single fixed copy of the discriminator, we build a complete TensorFlow graph describing k steps of the learning process for the discriminator. So the generator net is essentially looking into the future and predicting where the discriminator will be several steps later. And because it's the generator looking into the future rather than the discriminator looking into the future, we're actually setting a direction for that min-max problem. We're saying that it's max over the discriminator in the inner loop, and then min over the generator in the outer loop. And that very elegantly gets us around the mode collapse problem. Another really big important research direction for generative adversarial networks is figuring out how to evaluate them. This is actually a problem that's broader than just generative adversarial nets. It's a problem for generative models across the board. Models with good likelihood can produce bad samples. Models with good samples can actually have a very bad likelihood. And then even when we talk about good samples and bad samples, there's not really a very effective way to quantify how good or bad a sample is. There's a really good paper called A Note on the Evaluation of Generative Models that walks through a lot of corner cases to clearly explain all the problems with the different metrics that we have available for today. And then for generative adversarial networks, these problems are compounded by the fact that it's actually pretty hard to estimate the likelihood. There is a paper based on estimating the likelihood in submission to iClear, though. So that problem might be cleared up pretty soon once we have more experience with that particular methodology. Another research frontier is figuring out how to use discrete outputs with generative adversarial networks. I described earlier that the only real condition we impose on the generator network is that it be differentiable. And that's a pretty weak criterion, but unfortunately it means that we can't really generate sequences of characters or words because those are discrete, and if the output is discrete, then the function isn't differentiable. You can imagine a few ways around this. One is you could use the reinforce algorithm to do policy gradients and use that to train the generator network. There's also the recently introduced techniques based on the Gumbel distribution for doing relaxations that allow you to train discrete variables. Or finally, you could do the old-fashioned thing that we used to do. I saw Jeff Hinton on Thursday, and he was mentioning to me how this reminds him a lot of the way that Boltzmann machines were really bad at generating continuous values. So what we would do there is we would pre-process continuous values to convert them into a binary space, and then we'd use Boltzmann machines from there. So you could do the same thing in reverse with generative adversarial nets. You could have a model that converts these binary values to continuous values, and then use generative adversarial networks from there. You could, for example, train a word embedding model and then have a generative adversarial network that produces word embeddings rather than directly producing discrete words. One very interesting extension of the discriminator is to actually make it recognize different classes. And this allows us to participate in an important research area of semi-supervised learning with generative adversarial networks. Originally, generative adversarial networks used just a binary output value that said whether things are real or fake. But if we add extra outputs, saying which class they belong to, and then having one fake class, we are able to then take the discriminator and use it to classify data after we've finished training the whole process. And because it's learned to reject lots of fake data, it actually gets regularized really well. Using this approach, Tim Salomons and I and our other collaborators at OpenAI were able to set the state of the art on several different recognition tasks with very few labeled examples on MNIST, CFAR10, and SVHN. Another important research direction is learning to make the code interpretable. Peter Chen's InfoGAN paper here at NIPS actually shows how we can learn a code where different elements of the code correspond to specific semantically meaningful variables like the position of an image. Another research direction is connections to reinforcement learning. Recent papers have shown that generative adversarial networks can be interpreted as an actor-critic method, or used for imitation learning, or interpreted as inverse reinforcement learning. Finally, if we're able to come up with a good algorithm for finding equilibria in games, we can apply that algorithm to many other places besides generative adversarial networks. Things like robust optimization, literally playing games like chess and checkers, resisting adversarial examples, guaranteeing privacy against an attacker who wants to thwart your privacy, and all of these different application areas are all examples of games that arise in artificial intelligence and might be improved by the same kinds of techniques that could help us to improve generative adversarial networks. We're very close to out of time, but I'll give you 5 minutes to do this exercise, and I'll answer the last set of questions during the exercise. This exercise is jumping back a little bit to earlier how I described that there's a different cost function that you can use for maximum likelihood in generative adversarial networks. And I think this is a really good closing exercise because it really drives home the point that the key mathematical tool generative adversarial networks give you is the ability to estimate a ratio. And to see how that ratio estimation works, you are going to derive the maximum likelihood learning rule. In particular, we have a cost function for the generator network, which is an expectation of x sampled from the generator, and then applying f of x. And we want to figure out what f of x should be to make this cost function give us maximum likelihood. As a hint, you should first start by showing the following, that the derivatives with respect to the parameters of the cost function are given by this expectation of f of x multiplied by the derivatives of the likelihood. And if you'd like, you could actually just take that as a given and skip to the last step. At the very end, what you do is you should figure out what f of x should be given this fact about the gradients. If you can choose the right f of x, you can get the maximum likelihood gradient. So I'll give you a few minutes to work on that, and I'll take a few questions, and then I'll conclude.
Okay. So in your previous about the generative network, you mentioned that there is an important assumption that the function should be differentiable. But see, what if the function is non-differentiable? Because in some areas, such like bioinformatics, the data is some categorical label, not a numerical value, so it's non-differentiable. So in that situation, how to generate synthetic data using GAN network?
So there haven't been any papers actually solving that problem yet. I talked about this a few slides earlier, and my recommendations are to try the reinforce algorithm, to do policy gradients with discrete actions, to try the concrete distribution and Gumbel softmax, which are two papers that were recently released about how to train models with discrete outputs, or to convert the problem into a continuous space where generative adversarial nets can be applied.
I have a rather theoretical question. So the way I understand GANs is that it's very powerful in capturing the modes of a distribution, right? But it's not really truly understanding what images are, as in these Z's, you start from Z, go to generate X, right? So the question is, if you increase the systems, increase the image size, assumably the modes of the distribution are going to increase exponentially. So ultimately, if you have a, practically this may not be a solution. This may not be a problem. Maybe we just care about 100 by 100 pixel images. But let's assume I'm interested in 2,000 by 2,000 pixel images. If I truly understand what images are, how images are generated, there is no difference between 100 by 100 and 2,000 by 2,000. I can, that ultimate machine. My question is about way down the future. I mean, at the end of the day, you're capturing modes of the distribution, but this mode is going to explode if you go to larger images. So at some point,
well, the good news is that the modes of the model also have an exponential explosion as you use a bigger convolutional net. So if
but
you...
convolutional net, I mean, I don't want to repeat the same structure. I mean, the question is the modes of the distribution, right? At the end of the day, you are capturing the modes of the distribution.
Well, yeah, but a larger model can capture more modes. I guess the nice thing about natural images is that when you increase the resolution, you're looking at a different level of detail. But within the same level of detail, the same structure is repeated all across the image. So say that we've been studying 64 by 64 images, and we couldn't really see the individual furs, like hairs in an animal's fur. And then we move up to a higher resolution, and we can see their fur. At the higher resolution, we don't need to relearn the distribution over images of fur at every pixel separately. We learn one level of detail that can be replicated across the whole image. And we generate different z values at every x and y coordinate that randomly decide, fine details of the fur, like which angle it should be pointed in and things like that.
Why do you think in practice GANs don't scale up well when you go to larger images?
Well, you might be surprised by what comes in a few slides. Yeah, I think I should probably move toward the conclusion now. So recalling exercise 3, we're looking to design this f of x, this cost function that's applied for every example generated by the generator in order to recover the maximum likelihood gradient. We start by showing this property that we can write down the gradient of the generator in terms of an expectation where the expectation is taken with respect to generator samples, and we multiply f of x by a likelihood gradient. That's relatively straightforward to show. The basic step is to turn the expectation into an integral, use Leibniz's rule, which means you have to make a few assumptions about the structure of the distribution involved. And then finally, we take advantage of our earlier assumption that the generator distribution is non-zero everywhere. That allows us to say that the derivatives of PG are equal to PG times the derivatives of log PG. So that gives us this nice expression where we can get gradients of the likelihood in terms of samples that came out of the generator. But what we'd really like is gradients of the likelihood in terms of samples that came from the data. So the way that we're able to do that is importance sampling. We have this f of x coefficient that we're able to multiply by each of the gradients. And we can fix the problem that we're sampling from the generator when we want to sample from the discriminator by setting f of x to be p data over p generator. And this means that we'll have kind of bad variance in our samples because we're sampling from the generator and then reweighting everything to make it look like we sampled from the discriminator. But in theory, this is unbiased. From there, it takes a little bit of algebra to figure out exactly how we should take the discriminator and implement this ratio. We recall that the optimal discriminator gives us this ratio p data over p data plus p generator. And doing a little bit more algebra, we can rearrange that to say that we need to set f of x to negative e to the logits. This is maybe a lot to absorb right now, but I think it's pretty intuitive once you've worked through it slowly on your own once. And it gives you an idea of how you can take this ratio that the discriminator gives you and build lots of other things with it. So to conclude the talk, I'd like to show you some really exciting new results that came out using generative adversarial networks, and that kind of addressed the last question we had about whether generative adversarial networks scale to very large images. A new model just came out last week. I seem to have this curse that every time I have to give a talk about something, an important new result comes out right as I have finished my slides. So I desperately made some new slides on the plane on the way here. Plug-and-play generative networks, or generative models, sorry, make 256 by 256 high-resolution images of all 1,000 classes from ImageNet and have very good sample diversity. The basic idea is to combine adversarial training, moment matching in a latent space, denoising autoencoders, and Monte Carlo sampling using the gradient. And the really cool thing is they also work for captioning, or inverse captioning, where you generate images by giving an input sentence that describes the image. Overall, the basic technique is to follow a Markov chain that moves around in the direction of the gradient of the logarithm of p of x and y, with y marginalized out. You can use denoising autoencoders to estimate the required gradient. But to make the denoising autoencoder create really good images, the autoencoder needs to be trained with several different losses. One of those losses is the adversarial network's loss, and that forces it to make images that look very realistic, as well as images that are close to the original data in L2 space. This confirms some of the tips that I gave earlier in the talk. For example, in the tips and tricks section, I said that you often get much better results if you include class labels. We see here that plug-and-play generative models don't make nearly as recognizable of images if we generate samples without the class. We also see that the adversarial loss is a really important component of this new system. If you look at the reconstructions of the denoising autoencoder, we begin on the left with the raw data. In the middle, we show the reconstructed image. And on the right, we show the reconstruction that you get if you train the model without the adversarial network loss. So adversarial learning has contributed a lot to the overall quality of this current state-of-the-art model. So in conclusion, I guess I'd hope that everyone remembers that generative adversarial networks are models that use supervised learning to approximate intractable costs by estimating ratios, and that they can simulate many different cost functions, including the one that's used for maximum likelihood. The most important research frontier in generative adversarial networks is figuring out how to find Nash equilibria in high-dimensional, non-convex, continuous games. And finally, generative adversarial networks are an important component of the current state-of-the-art in image generation and are now able to make high-resolution images with high diversity from many different classes. And that concludes my talk, and I believe that we're out of time for questions because we already took several of them in the exercise breaks. And I think Aaron will now announce that we are headed to sign textbooks, and I hope you know what room we're signing them in.